Welcome back to another statistics video. In this video, we are going to focus on linear regression. So we need to talk about some terminology before we start that. First off, correlation. A correlation exists between two variables when the values of one variable is somehow connected to the values of a different variable. When we talk about linear correlation, we're talking specifically about creating a straight line that could be used to predict values or make predictions. Now, the linear correlation coefficient is how we measure how good of a fit that line is, and we use the value R to talk about that. And we're going to use technology. We're going to use StatCrunch again to figure out what the R value is. So there's a lot of things that can have a correlation. There could be correlations between age and height. We know that the older you are, you tend to get taller, especially when you're a child going up to an adult. And then it starts to level off there. So it's not linear always, just linear in the beginning. Or there's some kind of correlation there in the beginning. We could talk about height and shoe length. There's a correlation between those variables. We could talk about maybe GPA and incoming GPA from high school into college, and then GPA after your first year, and we could determine, is there a correlation between that? Or maybe we could look at ACT scores and GPA and ask, is there a relationship between those variables? So we're looking at two variables that may have some kind of correlation. We won't know that until we start digging into the data and analyzing the data. So if we look at just a few pictures, so these are scatter plots. We plotted X and Y data. X-axis is your horizontal axis, Y is your vertical axis. So notice the data points here. They're not in a perfect straight line. Notice our correlation coefficient is positive. It is a positive 859 there. Now, back in an algebra class, you probably did linear regression, and you said that if R was really close to 1 or really close to -1, then you had a really good fit. But we didn't say how close does it have to be. That's the question that we're going to answer in this chapter. There's our question. I'll call it Q here. How close to 1 or -1 does that R value have to be in order to have a good correlation? Is 0.859 good enough? Is -0.971 good enough? Now, the closer it is to 1 or -1, the better fit it is for the data. So we've got a bunch of data points here, and we've got a positive correlation. Notice that if we were to think about fitting a line in here, our line of best fit may look something like that. It would have a positive slope. The sign of the slope and the sign of the correlation coefficient will always be the same. So they'll both either be positive or they will both either be negative. Here, look, we have a negative relationship between these variables. Notice that correlation coefficient is closer to -1, which means that this is going to be modeled probably reasonably well by that linear best fit line, that regression line. And so it would look probably something like that. If we look at that third picture, notice everything's just scattered throughout. There's no correlation going on here because that correlation coefficient is so close to 0. And then if we look at that last picture, with the scatter plot, you can see that this doesn't even have a linear correlation. It looks more like a quadratic correlation, and that's reflected in that correlation coefficient that we've got an R close to 0.3, which is pretty low. So what are some of the properties of the correlation coefficient? Well, the first one is that the value will always be between -1 and 1. Okay, the closer it is to 1 or -1, the better fit it is for the data. How good, how close does that have to be? We'll answer in just a few minutes. The sign of the correlation coefficient will match the sign of the slope. Another property is that the choice for X and Y doesn't affect the outcome of R. So let's say we are analyzing height and shoe size. If we let X be the height and we let Y be shoe size, we'll get some R value. We'll get some R value. If we flip that so that we make this Y and this X, R will still be the same. Now, that regression equation will be different. You do have to be careful about choosing what's X and what's Y. But the correlation coefficient will be the same regardless. Another one, R is very sensitive to outliers. In fact, an outlier can make it or break it. It could make it where we have a correlation, or if we leave it out, it could make it so that there's not a correlation, or vice versa. We've talked about this already, but I'm going to write it down. R does measure the strength of the linear correlation. And we'll use R to determine whether or not that equation is even worth using. And then the last one. If we were to take all the values of X or Y and convert it to a different scale, maybe we wanted to take the logarithm of each of the values, that's not going to affect R. So that's interesting to note. So sometimes if you're reading a research paper or you're looking at some data, sometimes what will happen is they'll take the logarithm of all the X values or the logarithm of all the Y values. Usually it's the Y values. X is usually with respect to time. If we do that, that's fine. But what it does is it converts all of those Y values to a different scale. And if we were to do that and then compute R, we're going to end up having the same R value, whether we use the original or whether we take the logarithm of each of them. Which means our relationship between the two isn't going to change. And by that, I mean we're answering the question, is there a relationship between the two? So how do we know if there is a linear relationship? Well, what we're going to do is we're going to compare the R values to critical values. And we're going to use this table. This is in your textbook. it is based on what's going on with n and then what's going on with alpha. Now, in our textbook, if alpha is not listed, then they just assume we're going to use a 0.05 for our alpha value. Remember, this is the level of significance. So it's a real simple comparison. We're going to look at the absolute value of r. And the reason we're looking at the absolute is because we want to compare positive numbers to positive numbers. So if the absolute value of r is greater than the critical value that's from the chart, then we say there's a correlation. If it is less than, which means that critical value is larger than whatever the r value is, then there is not a linear correlation. Now, there could be something else. It could be quadratic. It could be, some other type of relationship, or there may not be a relationship at all between those variables. That's really for you to look at the scatter plot to determine. And then we could talk about r squared. R squared is called the coefficient of determination. And it's really just measuring the proportion of variation in y that can be explained by the linear relationship between x and y. So we're not going to really dive into that. What happens is your software is actually computing r squared. There's a formula that goes with that, and then it takes the square root of that to find r. R is the important value. This is just giving us a proportion that can be measured by the linear relationship there. So let's talk about some common errors. Do we have to be careful about correlation? And the answer is yes. For one, we cannot assume that correlation implies causation. Sometimes there could be a lurking variable that's responsible for that regression to go on. Remember, a lurking variable is something that isn't measured in the original study, but it could affect the outcome. Another one that we have to be careful about is using data that's based on averages. Remember, when we take an average, like the mean, we are suppressing outliers, and that could inflate the correlation coefficient. And then ignoring the possibility of a nonlinear relationship. That's why the scatter plot is so important. We want to use the scatter plot to our advantage, because if there's something other than a linear relationship, then we want to measure it in what it would actually be. Like, for instance, going back to this, that correlation coefficient is very low for this, but notice it's not even a linear relationship. This is measuring a linear relationship, but clearly we have something else going on here, probably a quadratic function there.